So we're going to talk about collisions now. Mostly when you think about collisions, you think about car crashes, so car collisions. And so I thought this would be an interesting picture to kind of introduce the idea of two objects that are hitting with certain momentum, and then when they hit, there's this transfer momentum. So this is a car crash that's from a large semi-truck and a little smart car. So this is actually a smart car. And what we found out from this accident is this driver was like, middle-aged and was texting while driving and swerved over in front of the truck, and the truck went on top of the car. So you can look up this accident to see exactly what the guy in the car looked like, but I'm sure you can guess what happened to him. So collisions are whenever two objects collide, the momentum is transferred or divided between the objects. So momentum is transferred or divided between the objects. This is called the law of conservation of momentum. So what it means is that the momentum before is equal to the momentum after. So momentum before equals momentum after. And so we'll see how this plays in terms of those collisions. A really, really good example of this idea of conservation momentum is a Newton's cradle. So in a Newton's cradle, if you pull back one of the balls, then the ball on the other end will pop back up. So one pops, one pops. Now what he's going to do is pull back two. So now the two balls have a certain amount of momentum. You notice that it's transferred through all of the balls, and two of the balls on this side pop out. And if he does three, then you get three on the other side. So whatever the momentum is in the beginning is transferred to the other side, the exact same amount. And then to prove that everything is normal, goes back to 1. And so one type of collision, there's two types of collisions. There's elastic and inelastic. And so we're going to start with elastic. And elastic is whenever two objects collide and the kinetic energy is conserved. So we'll talk more about kinetic energy in the next unit, but just know that kinetic energy is conserved. The way we look at this in terms of momentum problems, collision problems, is that the objects hit each other and then separate. So we start with two objects, we end with two objects. So the truck here hits the car, and in the end, they both bounce off each other. Now this is not very realistic because this is not what happens. There's crumpling that happens and stuff like that, but the idea, real life examples would be like a pool table or billiards, where whenever you hit one of the balls, then it transfers its momentum, the cue ball transfers its momentum to all of the different colored balls. Another one would be like croquet, where once again you hit one and it just bounces off the other, so directly transferring momentum. So to figure out elastic collisions, here's our elastic collision equation. And what you notice is mv, so m times v is momentum. So the initial, which is what the little knot means, so the initial momentum of the first object plus the initial momentum of the second object is equal to the final, that's the F, final momentum of the first object plus the final momentum of the second object. So however much momentum we had in the beginning between our two objects, we will have in the end between our two objects. So momentum is conserved. Momentum in the beginning is equal to momentum in the end. So why don't we try an example out of using our new equation. And so in this example, we have billiards. So we have a cue ball, and then there's a striped ball. So it says a 0.17 kilogram cue ball. Kilograms measures mass. And since this is the first one I came to, I'm going to make that M1. Is moving, so this cue ball is moving at 2 meters per second. So this also goes with the cue ball. So since it's meters per second, that's going to be our V1. And since this is what's happening initially, V1 naught. and hits the back of a 0.16 kilogram striped ball. Let's use a different color here. So here is our second object in the collision. So that is our mass 2, because it's in kilograms. And this ball is already moving at 0.7 meters per second. So 0.7 meters per second. So this is going to be our V2, and this is what is already happening, so that's our naught. If after the collision, so this is what happens afterward, both objects separate, this is your key phrase right here. Objects separate. That means it's inelastic. So both objects separate, and the cue ball is still moving forward at 0.4 meters per second. So that goes with the cue ball, which is 1. So after the collision means that this is going to be V1F. It's what happens after. So we want to know what is the velocity of the striped ball. So we want to know V2F. So I know this looks like a lot, but it's just one of those where just read it and figure out what goes with what. So like this mass goes with this velocity. This mass goes with this velocity, and so on. So here we go. M1 V1 naught plus M2 V2, oh, let's use colors here. Plus M2 V2 naught equals M1 V1F plus M2 V2F. So M1 is 0.17, so 0.17 times its initial velocity, which is 2, plus M2, which is 0.16, times its initial velocity, which is 0.7, and that is going to be equal to M1, which again is the cue ball, so 0.17, times its final velocity. So since it's moving forward, it's just going to be 0.4 plus M2, which is the striped ball, 0.16, times V2F. That's what we're looking for. All right, so what we're going to do is go ahead and multiply all this out. So 0.17 times 2 gives you 0.34 plus 0.16 times 0.7, which is 0.112, and that is equal to 0.17 times 0.4, 0.068, plus 0.16 times V2F. So now we're going to combine these two, add them together. So 0.34 plus 0.112 gives us 0.452, and that's still equal to 0.068 plus 0.16 times V2F. So now, in order to get try to get this V2F by itself, let's get rid of the 0.06. So we're going to subtract 0.0668 both sides. And it's down a little bit. There we go. And so here we get 0.384, and that's equal to 0.16 times V2F, and then we divide by 0.16, and we get a V2F of 2.475 meters per second. All right, so here's another example. So let's use some different colors now. So we have a 0.5 kilogram croquet ball moving at 1.6 meters per second. So those two go together. Since this is the first one we find, this will be M1, this will be V1 naught. That's what it's happening in the beginning. It hits another croquet ball at rest. So we're assuming that all croquet balls are the same mass. So this will also be mass 2, and at rest is going to be our V2 naught. Excuse me, V2 naught. If after the collision, the first croquet ball moves back with a velocity of 1 meter per second, what is the velocity of the second ball? So this is where we have to talk about the idea that momentum is a vector quantity. So if it's going forward, it's going a positive velocity. If it's going backwards, it's going a negative velocity. So it's moving back with a velocity of 1 meter per second. So this is the first croquet ball, which is red. And so we're going to go ahead, and since it says moving back, we're going to make this negative because it's going back at 1 meter per second. So that's V1F. And we're looking for the velocity of the second ball, so V2F. So I'm not going to write out the equation again. I'm just going to go ahead and start working it out. So 0.50 times our initial velocity, 1.6, plus our another croquet ball, 0.50, times rest, which is 0, equals 0.50 going a negative 1 plus our second, which is 0.50, times V2F. That's what we're looking for. All right, so 0.5 times 1.6 is 0.8 plus 0 equals negative 0.5 plus 0.5 times V2F. So now we add these together. We get 0.8 plus 0. So we're ending on green. This will be 0.8 equals negative 0.50 plus 0.50 times V2F. So since it's negative 0.5, then we're going to add 0.5 to both sides. And so this side we get 1.3 equals 0.50 times V2F. And so then we get a V2F of 2.6 meters per second. So now let's talk about inelastic collisions. So inelastic collisions are collisions where kinetic energy is lost. So energy is lost in some way. The way that we look at it in terms of equations is it's whenever the objects remain attached or are coupled together. So that just is another word for attached after the collision. So in my little diagram here, we start with the truck separate from the car, and when the truck hits the car, then they travel together. This is more like what actually happens in a car crash. And what I want you to notice is initially the truck's going 20. After it hits the car, it's now going 15. So whenever they couple together, since this one is not moving, this one is moving, it's going to slow down in terms of the grouping of them together. So for inelastic collisions, this is our equation. This side is the same. We start with two different objects. So M1 V1 naught plus M2 V2 naught. That is equal to the two masses together, right? Because they couple together, they join together. So M1 plus M2, and that combined mass has a certain velocity in the end. Just like here. They join together, the masses together have a certain velocity. See, same velocity here, 15 and 15. So here we go. A 3,000 kilogram car moving at 50 meters per second. Okay, so we have a 3,000 kilogram, so that's M, we'll say this is 1, is moving at 50 meters per second, so that's V1 naught, because this car is moving this speed. Rear ends a 2,000 kilogram car, so 2,000 kilogram, M2, moving at 35. So this car is moving this speed, so V2 naught. If the bumpers of the cars become attached, so there is your key phrase, attached. This implies inelastic. So for elastic, it was pulls apart or separates or something like that, where you know that they hit and pull back apart. The word attached, coupled, another one, so coupled, join, something like that, where it's implying that the two objects are becoming attached, are together after the collision. We want to know what is the final velocity of the two cars together. So there's only one final velocity now because the two objects are together. So M1 V1 naught plus M2 V2 naught equals M1 plus M2, because the two masses are going together, times their final velocity together. So M1 is 3,000, V1 naught is 50, plus M2 is 2,000, times its velocity of 35, and that's equal to M1, which is 3,000, plus M2, which is 2,000, times the VF. So 50 times 3,000 gives you 150,000, plus 2,000 times 35,000, or times 35, gives you 70,000. That's equal to the combined mass, which is 5,000, times VF. So all I did was add these two together. So these two combined, 150,000 plus 70,000, gives you 220,000. That's equal to 5,000 times VF. And so we divide by 5,000, and we get 44 meters per second. All right, so here's another example. So we've got a 1,000 kilogram car hits a 2,000 kilogram car at rest. So the 2,000 kilogram car is at rest. So we'll go ahead and label this M2. Here we go, M1 kilograms. First one is M1. M2 is at rest, so V2 naught is 0, since it's at rest. The 1,000 kilogram car has an initial velocity of 40, so that's our V1 naught. If both cars become entangled, so there's our key word for inelastic, what is the final velocity, so VF, of the two cars? So once again, M1, which is 1,000, times V1 naught, which is 40, plus M2, which is 2,000, times V2 naught, which is 0, equals M1 plus M2 times VF. So 40 times 1,000 is 40,000. This is 0, so it goes away. And we're left with this side, which is 1,000 plus 2,000, 3,000 times VF. So we're going to divide by 3,000 on both sides, and we get a VF of 13.3 meters per second. So the last thing to talk about is recoil. And this is whenever objects start together and then separate. So, for example, a cannon. So in this short little snippet, this is a Civil War reenactment where they actually used full artillery in the cannons. And so cannons are always on some sort of roller on the wheels, because if it wasn't, then that recoil would actually break the cannon apart because of the sheer force involved. So here we go. So it's going to be really quick. So what I want you to do is watch this cannon in the center. And so as soon as the cannon goes backwards, because the cannonball goes forwards. It's because there has to be conservation of momentum. So let's see how this works in terms of what we just saw with the cannon. So the momentum in the beginning has to equal the momentum at the end. So in the beginning, we have the cannon plus the cannonball within the cannon. Those are together with a certain initial speed. So cannonball is in the cannon, so the masses are together. Then in the end, we have the cannon going backwards, and we have the cannonball going forwards. So what do we know about the speed before? Well, the cannon was just sitting there. So since it was sitting there, this is 0. So this whole side of the equation is 0. So it's 0 equals m1 v1f plus m2 v2f. And so what we notice is that these have to be equal and opposite. So does that sound familiar? Newton's third law. This is where those forces involved come to play also with this idea of conservation momentum. Everything is related. So if we were to subtract this over, then this is what we would get, that the negative of one momentum has to equal the other momentum. Now, we really don't worry about this as much, and so we're just left with m1 v1f. So the cannon is equal to the cannonball. So since the cannon is so much more massive, then the velocity is really small. So this is a huge mass with a little velocity, whereas this is a little mass with a big velocity. That's why cannons are so big. So that's where this equation comes from. So don't worry about all of this stuff. This is what you need to be able to use for recoil, but this is where it comes from. It's still like a collision. It's like inelastic collisions backwards, where you start with them together and end with them apart. But the final momentums of each of the two objects have to be equal to each other. So here we go. Let's do an example. So we have a 500 kilogram cannon, so we'll make that our M1, fires a 10 kilogram cannonball. So again, you can already see the difference in the masses. And that cannonball has a speed of 200 meters per second. So the cannonball goes with the 200, so those are both 2's. We want to know, what is the speed of the cannon recoil? So speed would be v, and it's of the cannon, which is 1. So m1 v1 equals m2 v2, because they have to be equal. So we have 500 times v1 equals 10 times 200. So we get on this side 500 times v1, and on this side we get 2,000. So we divide by 500 on both sides, and we get a v1 of 4. So 4 meters per second. So here again, large mass, small velocity, smaller mass, larger velocity.